All right, good evening, everybody. This is Cathexis, and once again, I have Quantum Eraser with us. And what we're going to be going over today is probably one of John's favorite topics, and this is quantum mechanics and a couple experiments that demonstrate its validity and what the implications are, what it means. So, of course, as usual, he's got some really good quotes that back up these ideas, and we're just going to kind of go over the basics. Now, how you doing tonight, John?
I'm doing fine, sir.
That's good, man.
Ready to go.
Nice. Well, before we get going on everything fully, and what we're going to do is play a video. Now, this is fair use. We want to make sure that I want to say that, I guess. But what it is a basic understanding of the double slit experiment. And so this will be very helpful going in, even if you know it or not. It's just a short 5-minute video. So go ahead and we're going to watch this, and we'll talk about it a little bit when we're done, and then we'll get into the main presentation. So let me go ahead and put this up. And I'll be playing it from my speakers, so I'm going to stay open.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. Brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
And there you go, folks. And they say it seems
That's why this double slit experiment.
Sorry about that. And it seems mysterious to the materialist, is really what that interpretation is, in my opinion, where he said that at the end. So we're going to get into breaking this down a little bit. And John here's going to demonstrate another particular fail-safe experiment that explains this. Well, it validates this phenomenon a little bit more thoroughly. So I'm going to go ahead and present you now, John.
Okay.
And so just click share screen and you should be good. All right, I see you. And I'll make sure it's up on the link as well. 1 second. Yes, sir. We're good to go. So go ahead and take it away, and we'll go over some things after we're finished.
Well, thank you, sir. Well, that video was a good foundation point, just in case there were people that never heard of the double slit and never knew what it meant. I think that's a good foundation video on it. And it'll clear a couple things up, but then it raises so many questions. And that's what I wanted to present here for today. So as you can see, with quantum mechanics, all you have to do, it's kind of fun, is just utter these two little words to, at the dinner table or a family get together, and just look at the looks that you get. And they'll be looking like this. A lot of people be shaking their head and
there's so much mystic and woo-woo ideas and new age ideas that surround these ideas.
Yeah, even people that just casually hear the quantum mechanics, they had never even found out what those two words meant. They still get that look and start to shake their head like they do know.
Mm-hmm.
Which baffles me, but anyway, I like to do it. Every once in a while, when I get around a lot of people, I'll bring the topic up. Won't go into it any great depth, just to see their reaction. But that's what you usually get. So, why is that? Well, most neither have the time or the inclination to bother with such things. But for the layman who informally treads into this area, they're immediately confronted with numerous barriers. Some that we already talked about, the background noise. You get mathematical formalism, and like Cathexis said, the woo characterizations, and the snake oil prognostications. I really don't understand why that is. when I first treaded into this territory, but I quickly found out why.
Yeah,
So even
I
if,
have a pretty good theory myself. I think we'll go over that later because I think it illustrates
okay,
the lack of understanding of a materialist paradigm that they come up with all these erroneous ideas. But anyways, go on, John.
okay, even if you go the formal institutional route, at university, 99.999% of your undergraduate and graduate level studies will fall immediately into this core category: to shut up and calculate. We've heard this term before. I think Richard Feynman was the first one to coin the phrase, but from Nicholas Geeson, he's a professor of physics at Geneva University. He says, in short, then, the mathematical formalism of quantum theory provides no explanation. Why? Well, we talked about this before. Mathematics can only describe.
Mm-hmm.
He goes on to say, only a way of doing calculations. That's all it does. Some physicists conclude that there is nothing to explain. Shut up and calculate, they would advise us. Wait a second. This is physics. We need explanations, not descriptions. Any idiot can describe something. It takes a little different category and a little bit more acumen to explain something. And like I said, why is that? Why is there nothing to explain? Well, there's a means to their ends. Since the majority of scientists, which most professing are not, have an a priori adherence to their fairy tale religion, material realism, and atheism, the irrefutable experimental evidence in the literal thousands without exception of quantum mechanics, the most successful branch of physics in history, stands in direct contradiction to it. That puts them in a very uncomfortable position, vice-like, because you can either reckon with the scientific evidence, and there's boatloads of it, and adjust your worldview accordingly, or you close your eyes, put your fingers in your ears, and say, shut up and calculate, la, 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 over and over, and let the cognitive dissonance rule the roost. Then what you do is you start erecting barriers and start labeling it. Quantum weirdness, spooky, strangeness, absurdity, paradoxical, bizarre. These are all the watchwords. This is what you're going to hear. Even Dr. Quantum before said something about it. The weirdness. Yeah, it's run for the hills. Who's going to stick around then? See, that denotes a fringe science, which is the exact opposite of what it actually is. It surely is all of these. It's weird, spooky, strange, absurd. It's all those, sure. If you're wearing materialist and realist and atheistic glasses, sure, take them off. But no, they then conjure up and float mind-numbing interpretations, what are rescue hypotheses. For example, many worlds, the old multiverses deal, that can never be falsified, as a get-out-of-incoherent-jail-free card to cloak their mind-numbing adherence to fairy tales with the facade of science, which are merely clumsily contrived just-so stories, to obfuscate having to give account for the ludicrous scientifically falsified stance. Well, they're busted, and they know it. So, Richard Feynman, he's pointed out that every statement in quantum mechanics is just a restatement of Heisenberg's uncertainty principle. Well, if that's true, well, what did Warren Heisenberg think about all this? Well, the first gulp from the glass of natural science will turn you into an atheist. But the bottom of the glass, who's waiting for you? That's his conclusion. So, well, let's get to it. In the following discussion, I'll be talking about photons to limit confusion, but everything I discuss applies equally to all elementary particles, atoms, and molecules. So let's head back to Richard Feynman again. This is pretty outstanding. He says that the entire mystery of quantum mechanics is in the double slit experiment. Well, thanks a lot, Richard. I mean, that kind of narrowed the field down a bit, right? So let's take a look. So here's what we get in the typical double slit experiment. In Young's double slit experiment in 1801, this one to the right is what he saw. He saw an interference pattern, right? But later on, and we'll get to this, if you look real close to the left pattern, this is no interference. This is like marbles going through the double slit, right? If you look real close in here, you can see that they're real tiny spots or quanta. That's where quantum mechanics gets its name. Oh, like digits, there's particles hitting here. Now over here in this interference pattern, if you could zoom in here, you're going to see the same thing. There are little particles, discrete chunks of energy and momenta that hit this photographic plate. See, the argument isn't whether particles are hitting here. That's not the argument, because that's what's hitting here. We're looking, the main idea is the overall pattern. The overall pattern of these. So what are these results telling you? Well, on the left, it's telling you that each photon acted as a marble when fired and went through either slit as a particle. On the right, it's telling you that each photon acted like a wave. Very important, the like part, when fired, and each photon went through both slits at the same time. Right? So you say, wait, what? How can it go through? How can it be in two places at once? That makes no sense. Overall pattern is either two columns. That's no interference or wave-like behavior. And as I said, in both instances, at the moment of detection, particles are hitting that detector or photographic plate. The problem? If they're Newtonian particles, we should only see no interference on the left over here, if they were just Newtonian particles. But we see interference to the right. That's a problem. The problem is, what are they when we're not looking, or better, knowing? And two, why is it when we look, that is, measure or to know where they are before they reach their destination, the photographic plate, the pattern changes, and we get a standard particle pattern here to the left. This is a really good slide. So, to the right is the Young's double slit experiment in 1801. There's no photon detectors in this experiment. So, they shone a light, they had a light source, and shown it, through a double slit, and they got an interference pattern on the back wall. So from 1801 till roughly 1910 to the 1920 area, everyone just assumed that light was a wave. That was it. However, some experiments in that time frame, the photoelectric effect and Compton scattering validated that, well, photons were particles. And they said, whoa, wait a second. These aren't particles. This isn't a particle pattern over here. What's going on? So, like he said, so physicists got wise. They said, okay, let's put what's going on at these slits right here? So they put photon detectors here. And guess what happened? Well, the pattern changed. And they said, well, wait a second. How can just, observing or knowing which path they went through change the overall pattern? So they were pretty stumped at all this. And so you had two camps. So you had the photon detectors are causing wave function collapse up here. Right? The only other thing is knowledge of the which path information is causing the wave function to collapse and give these two columns or not an interference pattern. Now, this is very important, this key point right here. Here's where a lot of confusion comes in. I want to iron this out right now. Please ensure that you recognize the distinction between photon slit detectors and the photographic plate. I usually call it as a catcher's mitt because there's a difference here. You have photon detectors, which are at the slit and detecting any photons going through the slit, and you have the background plate or the photographic plate. Those are two different animals, and there's so much confusion because people talk about detectors and they don't differentiate between the two, and that just breeds so much confusion. So I wanted to iron that out, and you'll see how that irons out here in a few minutes. So like I said, here's your two camps. There's only two choices here. So what they did was, to resolve the situation, the quantum eraser experiments were designed to settle the question on the mechanism of wave function collapse. So it had to take some time. In fact, it took the year 2000 till they got enough technology and the wherewithal to do the experiment. So let's go through the scientific method. So you got step one, observe a phenomenon. Well, photons, elementary particles, atoms, and molecules exhibit both wave-like, that's interference patterns, or particle behavior. That's no interference pattern. Step two, whenever you have a hypothesis test, you always have two hypotheses. One's the alternative and one's the null. The alternative is if the which path information is known or can be known, then we will observe no interference. Conversely, if the which path information is not known or it's erased and never can be known, then we will observe interference. And of course, the null hypothesis is if the environment, that is the slit detectors, is the mechanism for wave function collapse or causing it, that's called decoherence. Quanta with a physical measuring device, and in this case, like I said, it's slit detectors, not the catcher's mitt, then we will not observe any change in pattern between the catcher's mitts. These are called detectors, like I said. It breeds confusion, but these are catcher's mitts, and you'll see them here in a second. Detectors or catcher's mitts will denote no interference. Our independent variable in this experiment is inside the experimental setup. You're going to see that here in a minute. And it's the paths. You've got known paths, and that's D3 and D4, versus unknown paths, D1 and D2. I took the dependent variable right from the actual paper, and what it was saying was it was predicted that the joint detection rates, that's D0 and D1, and D0 and D2, that's R2, will show interference patterns when detector D0 is scanned along its x-axis. This reflects the wave property, both path of photon 1. However, no interference will be observed in the joint detection counting rates of R3 and R4 when detector D0 is scanned. All right, so that's pretty cut and dry. So to solve this issue and to answer which one of the two camps here was correct, the delayed choice quantum eraser was devised. And since this is kind of small on my screen, I'm going to switch over. Let's go to a bigger one. What's going on here? This looks pretty complex, but I'm going to try to break it down, and it should make some sense to you. It's pretty easy once you break it down. So over to the left, you have an argon pump laser over here. It's going to shoot one single photon at a time, not many photons. You have the double slit. You have a BBO crystal that's going to split that single photon into two entangled photons, and this Glenn Thompson prism is going to send them on two different paths. One of the sister photons is called the signal photon, is going to go to D0. We're not going to talk about that one for just right now. For this moment, we're gonna concentrate on this side. And the other photon goes on one of two paths, whether it comes out of slit A, the red path, or slit B, the blue path. Now, this photon goes on one of two paths. Now, before we go there, notice something over here that I didn't mention. There are no slit detectors here. That's very important because remember our question, or the two camps. One of them said the slit detectors were causing wave function collapse, and the other camp said no, it was the knowledge of the which path information. There's no slit detectors here. You cannot tell which one it's going through. It's impossible. It's very important to recognize right now. Now these detectors D1, D2, D3, and D4 are catcher's mitts. That is very important to understand. They're not photon slit detectors. All they're doing is catching these photons. So as you can see in this experiment, if a photon is fired, we don't know which slit it's going through. It's going to come, let's just use the red path. It's going to come down here, and it's going to hit one of these. These green things are half silvered mirrors, BSA, BSB, and BSC. The MBs are full silvered mirrors. They only reflect, whereas these half silvered mirrors, there's a 50-50 chance of the photon transmitting through or being reflected off. That's important to understand. So let's take a path. One photon is fired at a time. The signal photon goes to D0. The idler follows the red path. Well, as you can see, if it reflects off of BSB and hits D4, guess what? We know the path information, because there's absolutely no way a photon fired out of slit B can hit D4, right? And the same thing for D3. Due to the experimental setup, the only way that this detector can be hit in this experiment is if it came out of slit B. There's no way a photon from slit A can come out and hit D3. And there's no way a photon can come from slit B and hit D4. There's no way. There's only one pathway to hit these detectors. Conversely, let's take a look at D1 and D2. Let's go through one. So off the red path, it fires out, it transmits through BSB, reflects off MB, hits BSC, and hits D2. Right? So we don't know the path information because a photon fired out of slit B can do the same thing. It could come down here, transmit through BSA, hit MA, transmit through BSC, and hit D2. So what they're saying here is this path information to D1 and D2 is erased, or better said, it's obfuscated by the experimental setup. So what happens in this experiment is quite amazing. Remember, we have no slit detectors over here. There's no way to know which slit it went through besides where the photon ends up. Like I said, if it hits D3, well, we know where it came from. It came out of B. Hit D4, it came out of A. Every single time that a photon hits here at D4 or D3, we get no interference. Conversely, every single time the D1 or D2 is hit, guess what happens? We get an interference pattern here. It's acting as if, because we don't know the path information, it went through both slits. Just like the previous experiment that I went over before. And it gives an interference pattern here. And a D1. Here's the trip out. If you think that's wild, check this one out. Remember that other photon? The entangled photon, the signal photon, goes to D0. Well, its sister photon, the idler, goes on its path, like I said. The absolutely astonishing thing here is that signal photon hits D0 8 nanoseconds before any of these detectors are hit. In fact, that photon hits D0 before any photon even gets to one of the half-silver mirrors, either BSB or BSA. And guess what happens? This photon knows beforehand where its sister or idler is going to end up, because it perfectly correlates when this position here is scanned along its x-axis, the position, it states no interference every single time for D4 and D3, and interference between D1 and D2. There's never any interference patterns with D4 and D3, or vice versa. There's never any no interference patterns with D1 and D2. That means this is space. You can see the space here between these detectors, and time independent. Space and time are totally irrelevant in quantum mechanics. This is absolutely jaw-dropping. So let's go back. Let's see the results. As you can see, when the correlation between D0 and the rest of the catcher's mitts are compiled, look at what we got. Between R1 and R2, we have interference patterns. But R3 and R4 show no interference. So this is pretty easy. Analyze your results. Step 4. As you can see with the results above, the witch path information coming from either slit A or slit B was erased or obfuscated by the experimental setup for R1 and R2. So the photon acted in a way as if it went through both slits. It displayed an interference pattern, the same pattern as the traditional double slit experiment without slit detectors. For R3 and R4, the witch path information was known due to the experimental setup. It displayed no interference, the same pattern as the traditional double slit experiment with slit detectors. Since there weren't any slit detectors whatsoever in this experiment, that is, slit A and slit B path information was either known or unknown merely by the experimental setup for each R1, R2, R3, and R4 downstream catcher's mitt or detector. So let's go to step 5. Validate or invalidate the prediction. The alternative hypothesis is validated. There is no possibility that the slit detectors collapse the wave function. Why? Well, because there aren't any. Ergo, the prediction was confirmed. Knowledge of the witch path information solely collapses the wave function. The null hypothesis is falsified. See figure 1 and 2. It's over. Decoherence is incoherence. So the experimental conclusions. The existence of the witch path information alone causes wave function collapse. Decoherence, the physical interaction with measuring devices, the slit detectors, does not cause wave function collapse. Why? Well, there weren't any slit detectors. And 3, QM phenomenon transcend time and space. That is, space-time is bunk. That's why Einstein tried to debunk quantum mechanics, because it was debunking him.
Spooky action at
So
a
the
distance.
Additional confirmation, there's a few of them. There's probably hundreds of them. The 3 I picked out. But the big one is this one, the quantum erasure with the causally disconnected choice from PNAS. This not only confirms and validates the delayed choice quantum eraser, but validates the time component by 5 orders of magnitude, and the space component by 50 orders of magnitude. This was space, their experiment was space-like separated by 45 kilometers. Now this is the big one. The gobsmacking implication here is that not only are there no slit detectors at the double slit, but the witch path information isn't revealed from the photon's perspective until after the fact. The result, that is, the results are reconciled and compiled by the researcher. It could be days, weeks, months, or years. Here's the rub. The photon knew that you knew where it came from and where it was going to end up before it ended up, and changed its behavior accordingly. So, what's that sound like? That sounds a whole heck of a lot like omniscience, doesn't it?
A little bit.
It sure does to me. That is the gobsmacking implication. See, it went one step further, not only reconciling, our problem here, the photon to two camps, but it went one step further and to say, you better start over because there's a problem in Shangri-La.
Yeah, they're operating with the wrong premises.
Mm-hmm.
And that's why they can't make sense of this. That's why it's such a... It seems like mysticism to them. That's why they all turn to mystics, all these quantum mechanics. These theorists.
It is mysticism to them because remember, they have the glasses on, the atheistic, materialistic glasses. Yeah,
exactly.
It sure is crazy if you have those glasses on. Yeah.
Yeah.
So
I could
Professor
agree.
John Wheeler, check this out from Professor John Wheeler. This is years before this experiment even took place. These guys knew it. It begins to look as we ourselves, by our last-minute decision, have an influence on what a photon will do when it has already accomplished most of its doing. We have to say that we ourselves have an undeniable part in what we have always called the past. The past is not really the past until it has been registered. Or put it another way, the past has no meaning or existence unless it exists as a record in the present. That's why Niels Bohr said, no phenomenon is a phenomenon unless it is an observed phenomenon. So a little sidebar here. That means all the fairy tale justo story prognostications, for one example, radiometric dating, or any dating method for that matter, by the metaphysical pseudoscience priest telling us what happened in the past, remember these guys, all these guys. This is all cod swallow, validated by experiment. So Rhodopiros, the moment at which we can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result. You see, the quantum mechanical description is in terms of knowledge, and knowledge requires somebody who knows. He is all over this. Alas, we live in a virtual construct. Who's the programmer or the knower? Gotta have one. In conclusion, in order for matter to exist, there must be a knower first. See, Martin Rees knew this. All these guys knew this, back in the day. Check out what he says here. Listen to this contradiction. In the beginning, there were only probabilities. The universe could only come into existence if somebody observed it. I would say who knew the path information. It does not matter that the observers turned up several billion years later. The universe exists because we are aware of it. See, these two are contradictions.
Yeah.
So hopefully he was saying this tongue in cheek. I'm pretty sure he was.
They usually do.
It has that tone to it.
Mm-hmm.
Like, come on, guys, let's get real out there without saying it, without explicitly saying it, just implicitly.
Right.
So let's get to some housekeeping, because there's been a lot of people I've been coming by trying to debunk quantum mechanics. I mean, I was laughing hard. And this has just been recent. Through the years, I haven't come about too many people. They may have some issues with the double slit experiment, but the delayed choice quantum eraser takes care of them.
It does.
Any comeback, anything they try to conjure is destroyed by the delayed choice quantum eraser. I haven't come up against one that it hasn't. That's why I call it the undisputed. So let's get back to this. To debunk quantum mechanics, This is tantamount to debunking water, by the way. So please, the first thing you want to do to debunk it, you need to take up the Quantum Randy Challenge. It's posted on Cornell's website. The Quantum Randy Challenge, henceforth QRC, challenges any pseudoscientist, you as it were, who claims that quantum physics is not true and that quantum entanglement experiments can be explained by a classically realistic and locally causal model. So what you get for your troubles, they're offering a Nobel, and whatever this is worth now, I don't know. I haven't checked that. But in addition to that Nobel, they're offering an additional $1 million US.
So they're trying to see if you can explain it in Newtonian.
Not only explain it, you need to show it by experiment.
Yes, but in a Newtonian way is what they're trying to say. Okay.
Because they know they can offer these things because they know they're not going to be able to do it because they have metric tons of truckloads of experiments all validating the same thing. So they know you're not going to be able to do it. So all you have to do is prove naive realism or local realism is true and not observation dependent. Yep. 4+ years now and still no takers. Well, I wonder why.
Yeah.
That's why. But if you do this, then this will happen. If you do this today, debunk quantum mechanics, then this will happen tomorrow. The understanding of all physical laws will collapse. Like Professor Shankar, the chair of physics at Yale, says, the laws of physics are always quantum mechanical laws. You don't have separate laws for big and small things. The real question is, how do these very same laws, when applied to big things, by big things I mean things you see in daily life, give the impression that the world is Newtonian? It's given the impression. If I give you the impression that I'm Superman, am I Superman? No, I'm not Superman. I'm giving the impression that I am. And by the way, say goodbye to current understanding of chemistry, biochemistry, and genetics. Number two, technologically speaking, we'd be plunged back to the dark ages. These and the associated industries would all implode in a nanosecond. Here's a short list. The entire computer industry, along with the internet, goodbye, all smartphones, lasers, fiber optics in general, spectroscopy, atomic clocks, and MRIs. Those will be going tomorrow.
Yeah.
From Scientific American, without quantum mechanics, there would be no transistor, and hence no personal computer, no laser, hence no Blu-ray players. The information age, of course, came about because of semiconductors and solid-state physics, which were enabled by quantum mechanics. Stephen Weinberg puts it quite nicely, I think. I'm tempted to say that without quantum mechanics, we'd be back in the dark ages. I guess more accurately, without quantum mechanics, we'd be back in the 19th century. Steam engines and telegraph signals. Why? Well, a big reason is because of this. Now, disregard completely orbits. These are not orbits. Electrons do not rotate around any nucleus. Okay, if you're unsure about that, I have a couple.
Yeah, it's just I think the misconception is they're just using it as a type of explanation or visual as to what may be happening, but people get confused. Well, it's atomism.
Yeah, I was taught this way.
Yeah, it's atomism, and I think that because heliocentricity and all this, there is a correlation to be made about the reason why they speak of it this way in our school books and such. So, but we should all leave that aside because it's not really how they work.
It's not what I wanted to talk about. However, let's
we'll get into that some other time for sure. But yeah, just I wanted to make that clear for the audience.
Yeah, we'll make it real clear, real quick from the organic chemistry textbook. This is university level textbook. Electrons are said to occupy orbitals in an atom. The term orbital is somewhat erroneous, as electrons do not orbit around the nucleus. These orbitals also do not really exist. They're only mathematical constructs. That's it. From Walter Lewin. He's the professor of physics at MIT. These discrete energy levels are frequently represented in high school and college level textbooks as circular orbits. They compare the electrons around the nucleus with planets going around the sun. And that doesn't even happen. In well-defined orbits. Yep, that's a misconception, for sure.
Exactly, yeah.
He says, for sure, they are not orbits.
Yeah,
so
they're energy
we can
levels.
disregard that right now.
Levels.
These, why I wanted to put this here is to explain a very important concept.
Sure.
That these are energy levels. This electron right now is sitting in the ground state. That's the relaxed state. That's what we like to be in all the time when we're sitting back watching TV. However, when atoms absorb, it has to be a discrete amount of energy. A certain amount, this electron will kick up into these different energy levels. Conversely, when it emits that energy, whether it comes all the way down to the ground state or does it in steps and release photons, by the way, what I'm trying to show you here is the quantum leap, and it's not the TV show. Whenever these electrons absorb and move up to these energy levels or emit and claw back down to the ground state, these electrons do not traverse the space in between. That's a very important concept to understand. If you understand that, you got quantum mechanics. At least 80% of it anyway. These do not traverse the space in between. And what does that validate? And how do we know that? Well, because of this. Spectroscopy. Emission and absorption spectra. You see, I have different atoms in here. I got sodium, hydrogen, calcium, neon, and mercury. So what this is saying is, you see these the discrete bands? They're called emission lines. And emission and absorption, which is right above, is the same. It's more or less the different sides of the same coin. So with these emission lines, energy, like everything else in this reality, is quantized. That means it's in discrete packets. If that electron traversed the space in between those energy levels, then all you would see from here all the way through is a smudge or a blur on each of these. Smudged and blurred. You could never tell anything. So spectroscopy, this really explained. They said, oh, got it now. This makes perfect sense. And like I said, if energy wasn't quantized and the quantum leap didn't exist, then instead of discrete emission and absorption bands, there would be a continuous smudge or blur through the differing wavelengths. That means every single element has a distinct fingerprint. And we can manipulate the electrical properties of the elements. And with the right mix in the amounts, what they call doping, boost conductivity, especially at the nanoscale. I also put in there, quantum tunneling, which we won't talk about, which is really cool. This is the basis for transistors. All they use for quantum tunneling is the interference experiment. Maybe at some point in the future we can get into that. Mm-hmm. It's very interesting. All they use is a proxy on that interference pattern. So from the University of Oregon, in principle, all of atomic and molecular physics, including the structure of atoms and their dynamics, the periodic table of elements and their chemical behavior, as well as the spectroscopic, electrical, and other physical properties of atoms and molecules, can be accounted for by quantum mechanics. Science. So you're still on the market to debunk quantum mechanics? You can pick a number behind Einstein. The line to the guillotine is quite short and it moves extremely fast, like at light speed. Also, another important key point. Photons create the electromagnetic field. They are not the product of EM fields. All electromagnetic radiation, that's the full spectrum from gamma all the way down to radio waves, are produced by photons.
Hmm. Yeah, there's a
Do
bit of a
not,
disconnect there.
yeah,
Sometimes I've
yeah,
seen.
yeah. That's a very important concept to understand.
Yeah.
And it goes back up to the emission energy absorption spectra. Yeah,
Mm-hmm.
yeah. Important one. Do not confuse EM waves of photons with wave functions, which we didn't get into too much here, or wave particle duality. So you can see how not only the detector point that I brought up above between the photon slit detectors and the catcher's mitt detector cause problems, this causes a lot of problems too. There's no doubt about that. So, the last gasp of the Wiki Google scientists on amateur night. You'll hear this constantly everywhere you go. Well, quantum mechanics doesn't apply to big things. Really? Well, from quantum interference of large organic molecules in nature communications showed that this molecule, as big as 5,300 atomic mass unit, that's 430 atoms, displayed interference.
Wow.
Photons here. I mean, this is massive, right? And if you think that's impressive, this one just scuttles that one. Particle physicists successfully placed a metal paddle 30 micrometers long, that's trillions of atoms, in a superposition of moving and not moving at the same time. A team of scientists from nature has succeeded in putting an armed object large enough to be visible by the naked eye into a mixed quantum state of moving and not moving. And this paper is by Aaron O'Connell. It's the quantum ground state and single phonon control of mechanical resonator. It's in Nature. And here's a video of it right here, of him personally talking about the experiment. Maybe I can hand that off to you, maybe put that in the description. In conclusion, quantum mechanics has taken the mytho-mathematics of Einstein, Newtonian mechanics, and the kung fu death group of materialists, atheists, the religious fairy tale that scientifically falsified belief system to the woodshed and bludgeoned them senseless. Phlogiston, 13th century alchemy, and Humpty Dumpty have more veracity. Have a nice day. Oh, side note, I forgot about this one. In 1924, Louis de Broglie, his doctoral thesis, he had a pretty eye-opening prognostication here. He said, well, see, if photons, which we thought were waves, are actually particles, then what if things we know are particles have wave-like attributes? So he then experimentally validated the same patterns and phenomena we've seen above with photons with electrons, which led to a Nobel Prize in 1929.
Yeah.
So
That's
I hope I explained this well. It's difficult explaining complex subjects simply. In fact, didn't somebody say back in the day that if you can't explain it simply, then you don't know it well enough?
I think 20
So,
minutes is pretty good on a subject like this. So I think you nailed it, John. Seriously.
I did the best that I could with trying to break it down.
Well, that experiment's a
And
bit complex in order
sure
to,
it is.
like really. And I think though that there's just one point I want to go back to concerning that experiment is
Sure.
those.
Do you want to go here?
Yeah, if you just keep it up, that'd be perfect. So
Yeah.
D0 is just collecting a split of each one of those beams, and it's going directly in, which means
It's
it is not going to be affected in any way, right? Like how do you put that again with D0?
so yeah, D0. So remember a single photon is fired. Two entangled photons are generated by this barium borate crystal right here.
Okay, and just
Then the
quickly,
path,
so the entangled photon, what exactly is that? Can you briefly explain that? I just want to make
that
sure
goes
our
down
audience
to,
understands it.
well, it gets into a complicated subject. It goes into spontaneous parametric down conversion. We don't want to go there.
Okay.
All it does is it splits that original photon that came out into two sister photons. One
Okay.
of the sister photons goes to D0. Its sister then goes on path A or path B.
Mm-hmm.
Now at this D0, this isn't just a catcher's mitt. You see this position X? Every time that this hits this detector, this position is scanned
Okay.
and identified. And then it's sent to this coincident counter here, along with all the other hits
Gotcha.
from the catcher's mitts. And then compares them, like the hit with D0, with the next photon hit. Because that's the next one to hit, because there's only one photon or
But
one
there
photon
is a time delay. So D0
Sure.
will be hit first, and then several
Yes.
nanoseconds later, or up to seconds, I'm probably nanoseconds, they can calculate it though. It will be hitting another one of the plates.
Yep, it's 8 nanoseconds. It arrives at D0 8 nanoseconds before any detector is hit. And in fact, that the sister photon doesn't even get to these half silvered mirrors. It's here. It's in here.
Yeah.
So how can this know where the heck that photon's going?
Yeah. It's quite
And it
troubling.
correlates every single time. There is no difference. It's either interference with D1 or D2 or no interference with D3 and D4.
And that's so great that was an incidental find about this. The real experiment was really just to prove those, the knower and the whole witch path information. This showing the entanglement, that they're doing it first.
I don't want to characterize it. I don't want to characterize as incident. I mean, this is a brilliant experiment.
Well, true. Yeah, I can't say that they probably weren't looking for that too, but I'm just saying at first glance. Yeah. But it's still a pretty amazing find.
That's it's the delayed choice part. That's what this part is. The quantum eraser part went to settle those two issues that we had before with the experiment. Remember? Yeah. Whether the photon detectors were causing collapse in the original double slit experiment that we talked about before. And it's really easy because there are no photon slit detectors. They just took it out of the equation.
Yeah, gotcha. Now this one, so the delayed choice quantum eraser, the one we're showing right now, who was that originally set up by, or group that set it up?
Dr. And I might want to give you the source for that.
Well, that's fine, but so you said that was recent. That was in 2000 that they finally got around to being able to do something like that. Is that right?
Yes.
So that dispelled a lot of confusion, then, essentially.
It did. But it seems I've been reading comments years before, just like I read with Professor Wheeler, and he's not the only one. They already knew this.
Sure, I'm sure they could infer it, through their understanding of it.
Yeah, but they didn't even it wasn't like they were questioning it. They were making firm statements, and I'm sitting there, well, wait a second. You haven't validated anything. So I don't know, maybe they were privy to other information, but it wasn't only Professor Wheeler, it was a ton of them. They were all stating things like this. But let me tell you something. Right here. I mean, this sent people off the deep end. You had physicists going in droves to the Eastern mystery religions. Why? Because they can't reconcile this
No.
experiment with their worldview. It's impossible.
Yeah, absolutely. I agree. Everything that you've
So,
presented in the past several shows has been pointing out the dogma of materialism and how these real sciences bust it up and show it for what it is. So it's a dogma and it exists very pervasively in our society, and it's being pushed by pop science, which is making it stronger. And it's a propaganda. It's materialist propaganda. We see it every day in our news streams. So that's why we're doing this. But I do want to quickly ask, and this is probably a contentious issue, and I don't know if we have a good answer for it, but I
sure.
mentioned it earlier. I see a lot of people in chat trying to say that light is not a particle, that saying
Really?
that it's a wave. Well, there's there's the idea that Wheeler puts forth, and there's several other people. It goes against the whole thing, but there's the idea of the ether possibly, and remember I mentioned it earlier, the perturbation to the ether. But then someone brings up the point of like, okay, well, let's say if I have a bunch of photons collected on a collection plate, is it going to weigh more? Are photons mass? Is there mass to
But,
photons?
but but listen here. All you have to do, there's thousands of experiments that show this. Just send one photon towards a photographic plate. Can you see this here? You see little dots.
Yeah. Now, but
You
how
know,
how do
when
they
a wave hits
isolate
you,
a single photon? I know that
they could
might.
do that these days. Back in the old days, what they did, it was a probability thing. They just made the light real dim, and they pulled the light really far back from the double slit, and they figured out the probability of when one photon will go through. But now they can do it intentionally, one photon at a time. I've seen hundreds of experiments, just one photon at a time. And this is real important. When if you're standing 5 feet in front of me and I throw a rock or a pebble and hit you right between the eyes, see, you're going to feel all that energy and momenta hit you in one discrete spot. See, but a wave, like a physical wave, like a water wave, the energy is spread out across the whole transverse dimension of the wave. If I hit you if I throw a bucket of water on you, it's going to hit your entire face. You're going to get soaked.
Okay. Yeah, I'm actually saying I looked it up too while I was asking you. It says, in a nutshell, by lowering the intensity of a light source to the point of zero emitted by the source and then slowly increasing it is what they've done originally. But now they have the detector. They have single photon detectors, and it looks like they've gotten better with their technology.
Yeah, that one experiment I sent you, you can't play it because you get a copyright strike for sure because Morgan Freeman's on it. But Anton Zellinger does it right in front of you.
Okay. Okay.
He does it right in front of you. He's got the laser and he starts firing, and you can see the little dots. Those little dots are discrete chunks, quanta of momentum. And electrons have the same behavior. If you don't know the Witch path information, guess what you're going to get? You're going to get this pattern right here.
Oh yeah, yeah, yeah. It's phenomenal. The implications are really powerful, and and it's so funny because when I was in that paradigm, that materialist, rationalist, atheist paradigm, quantum physics was spooky to me. That was the best. Well, I mean, I'm not meaning seriously, but I mean it was one of
Right.
these mystical things. And when I learned about it, I
And
was like,
how did you learn about it?
well, I had heard murmurings of it, and I saw that movie that we actually played the video from. What the bleep do we
Okay.
know? But that was in like 2004. Then I tried to read up about it, and I was just getting into college at the time when I discovered this stuff. But still,
Right.
there didn't seem to be a good answer for it. So that had this mystical quality to it. This is why the New Age attaches to it, because these people are coming out of a strong materialist paradigm trying to reconcile this stuff. So the only thing they think is that it has to be some mystical action going on
Well, you
or
see, there
whatever.
was no problem with the technology, right? See, there is no problem with that. There's no argument there. I mean, for all the technology, this is slam dunking it. It's over. The problem lies in what it means about the nature of our reality.
Yes.
That's where the argument is. And I told you that the argument is based on, for most physicists who are materialists, they can't reconcile it. That's why there's such a tension with it. Listen, take those materialist glasses off, we're good.
Yeah.
This lines up with idealism. So I don't know.
Yeah.
I mean, I had one guy the other day tell me he debunked the double slit experiment by showing single slit diffraction.
Yeah.
I was speechless.
Yeah, I saw that. And you know, there is there is a gentleman on here that a lot of people respect. I think that's who you're talking about, the Ken Wheeler gentleman, theory hypothesis. Who?
No, it wasn't. It wasn't Ken. I don't.
No.
It wasn't
He was referring to Ken Wheeler's ideas about quantum physics.
No, but he showed the video.
Yeah, that was one of the videos of him, Ken Wheeler.
Are you sure that's Ken Wheeler?
Yeah, that's what I had linked. I'm pretty sure. When the guy in the Hangout said it to you, and you went and looked further for it, and he brought the video he was showing was theory hypothesis, who is Ken Wheeler. His theory about quantum mechanics is that it is electromagnetic in nature, the ether, that light is a wave, it's not a particle. He claims he's a cameraman, and his camera doesn't weigh more after a day of shoots. You know, it's all of this line of thinking.
Well, what does he have to say about spectroscopy? I can just put this up. That's all I need.
No, fair enough. But I want to make it clear for the rest of my audience. I actually agree with a lot of what Ken Wheeler says. But after seeing this presentation and speaking with you, John, about this, I think Ken Wheeler is wrong about. You can be wrong about some things and be right about others. Because
surely.
Yeah, because I think he is right about a lot of other things. He talks about the electromagnetic nature of our existence, and that gravity is really a static electric effect, and it's not this mass drawing mass, which I agree with too. And
what did I say here? Photons create the electromagnetic field. They are just not the product of EM fields.
Yeah, well, it's the photons that are making up the field. Yeah, I understand that. Sure.
Yes. Yep. They produce the electromagnetic field.
Mm-hmm. Yeah, absolutely.
Yeah.
So I think there's a lot lost in translation. You know, I think a lot of people are disconnected from the scientific method, the validity of certain scientific experiments, if done correctly and repeated properly, like you've presented with quantum mechanics and several other sciences you've showed in the past. A lot of people are unaware of that level of consistency. They have more of a colloquial understanding of these topics. And so, like, I've even said that I've even heard people say that quantum physics is nonsense 100%, or the atom doesn't even exist, and we're just being lied to. And so you got people who go down this conspiracy aisle, and it is what it is. That's why I'm doing this, is to show this to the public.
Here's the problem, though. It's validated by the experiments are out there.
Mm-hmm.
You can go track them down.
You can do them for yourself. You can do these for yourself. Yeah.
That's the difference between quantum mechanics, real science, and cosmology, astronomy, astrophysics. They have no experiments.
Yeah.
That's what science is.
Experimentation.
Experiments.
That's right.
So good luck to you.
That's right. Yeah, I'm with you, man. And that's the reason why I think it's so important to point these and hit these topics like we have consecutively too, is laying a foundation of understanding of, the tools to help a person kind of realign their paradigm. There's just so much misinformation about what science is. People conflate scientism and pseudoscience into their worldview and treat it as science. This is what causes people to basically fall at the feet of the white coats because and then they'll come up, what's your credentials? How can I believe you? Well, how about the credentials you need to see is your own ability to critically think?
Yeah.
How about that? Let the people take the information, measure you on the merits of the knowledge that you're passing on, and then move on. Well, I don't understand what's so hard to take information from people. It's so strange how these guys operate sometimes. But yeah, I'm looking forward to next week
so
too.
listen, do yourself a favor and go through this experiment. Listen, I just went through this real quick, right?
Mm-hmm.
Get the original paper, go ahead and sit down and go through this. I mean, and critically think, okay, what's going on here? All right, I gave you a stepping stone to go here and go and critically think what is going on here. I mean, the simplicity of this experiment, it looks complex, like I said, but it's actually, once you get down to it, once you have a good understanding of it, it's really
actually
quite simple.
It is. It's really simple. Like, I remember when the first time you had showed it, I'm like, what the hell? And it just takes one or two Passovers to really understand the significance. And honestly, it took when you showed it to me earlier today, we went through the presentation. What was it, 30 minutes later that I had the damn epiphany?
Yeah,
I called
right.
you up and I said, are you kidding me? The entangled photon knows before the other one? I didn't even realize it.
Hey,
that's what's
yeah. You're not the first one.
Yeah, it's an impressive thing. It really is an impressive and staggering thing when you realize this and realize that this is real, repeatable science and the implications of it. But it takes a good while for somebody in a different paradigm to kind of evaluate what this means, and hopefully they can come to some better conclusions.
Well, and it's difficult for most people because, they're busy with their daily lives, and it's hard to take 2,000 hours out of your time and devote to focusing on these experiments, because you got to focus. I mean, they'll lose you pretty quick.
Sure.
But once you go through these, especially when there's help with illustrations, going through and explaining these experiments, you'll get it.
Yeah, I agree.
It's the implications that are going to rock your world.
Yeah, absolutely.
Yeah, that's the implicate. See, that's the part that most people have the biggest problem with, because it doesn't line up with what they previous believed, and that creates a lot of problems.
Yeah, because they had a Newtonian. Well, no, they actually believed it was a wave, right? So it up until what, 1901 or 1920 or so.
Yeah.
You mentioned that last quote.
Yeah.
So they did think it was a wave of energy, right? But
they thought it was a wave because it acted like water waves. But get into this here. When something's fired here, see, they described this. What Schrodinger did was, he was a graduate student. What he did was, he looked at all these experiments and noticed the pattern. It's real easy to notice because you got interference patterns every single time. And what he did was, he reverse engineered the experimental results and said, well, if this is the case, then this had to be going on back here. So he came up with a description of the wave function. See, the wave function is not a physical wave. There is no medium. Mathematical construct that explains the results of this experiment. That's it. Now, I'm not saying that it wasn't, yeoman's work, to get there. No doubt about it. He received the Nobel Prize for it. But that's what he did. So the mathematical description's fine. You can describe it all day long. Thank you very much. Now explain it.
Yeah.
See, his mathematical description was only describing the superposition. But if you think what a superposition is, you've got something is in superposition of itself. It's nonsense.
Yeah.
Something can't be two places at a single time. It's absolute nonsense.
Yeah.
So the mathematics or the formalism of quantum mechanics, see, nothing's derived. The mathematics isn't derived. It's conjured to explain the structure. They had to have a theoretical structure here, so they're just describing it. Well, descriptions only go so far. We need explanations. Why? The why and the how. Follow?
Yeah, I do. You know, so I just, what is Einstein's opinion on quantum mechanics? Didn't he try to disassociate
Einstein
it?
didn't. Yeah, because like I said, it destroyed space-time.
Yeah, it says right here, in 1930, Einstein argued that quantum mechanics as a whole was inadequate as a final theory in dealing with the cosmos.
Sure. Quantum mechanics, quantum mechanics and special relativity and general relativity are mutually exclusive. They're married bachelors on their faces. So he had to come around and try and with the EPR paradox, and try to debunk quantum mechanics. Because if he didn't debunk it, well, he got debunked. Well, he got debunked, and he got debunked in officially. John Bell came up with his Bell's inequality, and then that was experimentally verified in the early 70s, and then validated again in 1982 by Elena Spey. So that's it was over then. It was over way before that.
Yeah, yeah.
But you won't hear much about that.
Yeah, I'm seeing there's an article right here I just decided to look at. It said, what Einstein, oh, wait, hold on. Oh, yeah, Einstein versus quantum mechanics and why he'd probably be a convert today. And the opening sentence says, Albert Einstein may be famous for his equals MC squared, but his work also laid down the foundation, blah, blah, blah. His analysis. Okay, well, this wasn't the one I was thinking of, but they were basically the other ones I looked at were saying how he just thought it was ridiculous and too bizarre, and it doesn't work. Yet he was pretty much wrong. It just
it takes special relativity and general relativity to the woodshed.
Oh, listen,
I mean, third graders.
Sorry.
You don't even need quantum mechanics to take him to the woodshed.
You can take it. Yeah, you're right.
We already went over that. See the gravity video. I think it was one of our first videos with Jaron.
Yeah.
Just go to that video. I explain it to you there. It's over.
Yeah, it's actually in this article from phys.org. It says, at the time, most quantum physicists adopted the shut up and calculate philosophy. Get on with the job. Don't worry about the philosophical issues. Just get the predictions. Wow.
And their prediction, see, you can fire 1 million photons, electrons, atoms, molecules towards this double slit, right? You can, if I fired 1,000,001 photon, you cannot predict where it's going.
No.
See, those quantum predictions are probabilistic. This is a histogram, basically. Let me get another one. This is a histogram, basically. It's a probabilistic prediction. So it's not an exact prediction. See, there's a big difference there.
Yeah.
So probabilistic histogram, it's just a probability distribution.
Gotcha.
And quantum tunneling uses this knowledge for transistors, for electricity regulation. If you want to get into quantum tunneling, look up Josephson junctions. I mean,
we'll have to. You know what we should do is do like an episode of peripheral science, things that kind of apply to the topics that you brought up. Because there's been a couple things that have come up, that you said we'll talk about later. So we'll have to do like a summary of it soon. But Yeah, that's definitely one I want to get into further because there is a lot of unknowns when it comes to this, I think, for the public. And I know I'm learning a ton.
Sure.
So, um, but just quickly, next week, for everyone's listening, we're going to be doing kind of a summary show of where we have gone from to where we are now in a philosophical context. I'm going to be writing up kind of a presentation of sorts, going over each one of the topics that we've discussed and the implications. I might even have on another guest as well. I'm still thinking about how I want to do the show, but then from there, I think with those understandings, if you've been watching consecutively, I think you'll be able to kind of grasp the reason why we're going to approach topics like cosmology and some of the larger, um, which are really philosophically driven. And this is one of the biggest points I want to make, and how we can discuss it better and pull apart what a model is and what it isn't, and what reality is, and how they relate, and if they relate at all. This is all the stuff that I really want to get into with our next show. So I just wanted to put that out there for everybody. Um, I'm sure you'll be up for that, right, John?
Oh, no problem.
Yeah, yeah. We'll work on it, throughout the week. We'll be in touch, and I'll give you a couple ideas and see if we can bounce some ideas about back and forth. But
Okay.
is there anything else you'd like to add this evening?
I don't think I can add anything.
No, I think you said it all quite nicely.
I
So
appreciate that. Thank you.
definitely. So I'll go ahead and finish it up tonight. We'll make it another rather short one. Thank you, everybody who has been supporting us, everybody out in the live chat who's been listening. Like I said, we'll keep everybody posted on when we're going to put the information up. John wants to kind of compile everything in more of like a PDF so we can just kind of pop it out at once. So, do apologize for anybody who's been asking for the presentations, but it's his work. We want to make sure that he's covered in all ways. But anyways, everybody have a great night. Thank you so much for coming around and listening. You guys take care.